Okay. Same time. Okay. So, hi everyone. Today we will talk about practical problems of reinforcement learning. And as you see, the subtitle is How to Beat Your Colleagues at Video Games. And why do we speak about video games? Recently, we've seen a lot of very fancy stuff of gaming, like bots, which plays StarCraft, chess, Dota, hundreds of videos on YouTube, and so on. And basically, let's say you want to implement your own bot with some reinforcement learning solution. And maybe you just want to beat your friend or your colleague, or maybe you just want to test some algorithm and so on. So the question is how difficult it is. Is it doable? So that was the question that we had in our data science team at brumbrum. Basically, at lunch breaks, we played video games, and we are not so good, I must tell you. So we wanted to implement a bot, and we had the same question. So actually, the answer is it's quite doable. But let's just do one step at once. What is actually reinforcement learning? So as Wikipedia says, reinforcement learning is an area of machine learning concerned with how software agents act on a certain environment in a way that maximizing some cumulative reward function. What does it mean in practice? It means that, first of all, we have an agent. The agent performs some actions on the environment. The environment changes its state, and also sometimes gives or not gives a reward to the agent. And the whole goal of the agent is to maximize a total reward. So in video games, when you play against your opponent, he performs in an unpredictable way. That means that we have an environment with probabilistic nature. And let me introduce our case. We choose this game, which is called Haxball. This is just browser physics-based football. And why did we choose this game? First of all, because it was the game that we played a lot in the office. Then the rules are really easy, but the problem itself is not trivial. So you cannot apply just if-then-else logic to find an optimal strategy. So it's really hard. When one player plays against another, it's already a challenge, one versus one. And then, unfortunately, there were not any ready implementations, but still we had to beat our colleagues, and we wanted to implement it ourselves. So the conclusion is it's not too easy, it's not too hard. We will see why. And let's start with the problems you most likely face when you will want to implement your own algorithm. And the very first problem you will face is the program interface. In particular, your agent must perform actions in the game, in the environment. And so before asking yourself, how can machine learn to play, you must provide this mechanism. Your agent have to perform an actions, read the state, read the reward, and so on. So this part is usually overlooked in courses and conferences. In some cases, it's not a problem. For example, if we speak about Atari, this is a famous virtual environment provided by OpenAI, which is open source. You can just get it and start playing with it. In some cases, like for example, board games, for example, chess or Go, you can try to implement the logic of the game by yourself. In some other cases, like StarCraft, for example, you must really be a giant software house like Google, DeepMind, to have an access to the raw data of the game. But surely it's not us. And what about other cases? First of all, how do we humans interact with the game? Watching the screen, pressing the keyboard, the mouse, and so on. So one can think, let's implement computer vision algorithm on top of it. There are a few problems here. First of all, usually it means that you have to deal with the image output of the game. That means that you have to introduce more complexity to the structure of your algorithm. You will have to train more for more time. You will need more resources. Probably in the end, you will have worse results. Another case can be reading the network. For example, you can try to inspect the traffic, if it is online game, the traffic of the game, just reading the state, reading the action, and so on. But if all the traffic is encrypted, it's not even doable. And in some other cases, if the game is browser, if it is implemented in JavaScript, you can try to modify the source to do a injection. And that was our case. So we did use the Chrome API to render the game in the browser, to get the state from the JavaScript global variables. Means that we had to decrypt certain parts of the logic and reverse engineer the meanings of JavaScript variables. But after some work, this allowed us to read the coordinates of the ball, of the players, and so on. And to send the actions, we used Chrome API, just JavaScript keyboard events. So next problem is the reward function definition. Recall that the environment, along with the state, provides to the agent a certain value called reward. And the agent's goal is to maximize its total. In a biological system, you can see it as an experience of pleasure or pain, for example. So the environment tells the agent how good or how bad was the previous action. And why do we need reward function? We use it for training. In a game like Haxball, one of the possible strategy of training is so-called self-play training. That means that the agent plays against the copy of itself. And in the beginning, the agent knows nothing about the game rules, performs randomly, and then during the training, it may produce some good results. Self-play strategy for training was used for famous AlphaZero algorithm developed by DeepMind, when actually playing against itself, the algorithm learned how to play chess on the superhuman, even superbot level, just in 4 hours. Okay. So the reward is typically of two types. The reward is sparse if the agent receives it only when it reaches some target. A game like Haxball has seemingly clear sparse reward. It's a number of goals. However, sparse rewards make the training hard or even impossible. Remember that at the beginning it moves randomly, then it receives no hint from the environment, and until he reaches this target. So we can suppose it should reach the target, but it does not happen always. And we speak about shaped reward if the agent receives it positive or negative for every action it performs on the environment. In a sense, the agent knows immediately how good or bad was his previous action. And in this case, we can say that cumulative reward is continuous function, changes with time. Shaped rewards are often much easier to learn because they provide positive feedback even when the agent has not figured out the optimal strategy. For instance, in a racing game, we could provide the score instead of the victory. However, look at this GIF. This bot has to maximize the score, but as you see, it found a way to collect those green objects, and we cannot tell that this is the winning strategy, but it maximizes the score. And this teaches us that shaped rewards can be misaligned with the true goal. So, summing up, we have learned that in most cases, the reward function is not intrinsic to the game. You must define it by yourself. You must be very careful defining it. High accumulated reward does not always bring us to the intended solution, as we have seen with the bot example. Even if you come up with a good reward, the agent could learn a strategy which seems optimal to the agent, but it's not the best. For instance, look at this. As you can see, this half cheetah learns flip and maximizes its velocity, but in a very strange position. And it moves at about 1/3 of the speed it would do if it was in a correct way up. So just be ready to spend a lot of time for so-called reward hacking. This brings us to our own experience. We saw already that just counting the goals is not the good way. The reward is too sparse. In this GIF, you can see what happens when we just define the reward as the negative of the distance from the ball to the opponent's goal. So they just get stuck. And I must tell you that in these examples, the agent plays against itself. Okay? Another example. Okay, here, for example, we punished the agent for long times. So what happened? The blue player prefers just to escape from this strange situation when it gets huge negative reward, and lets the red just score. Okay, then another case. Here, we penalize the distance to the ball. So the agents learned that if they got too close to the ball, one can kick away the ball by chance. It's probabilistic, okay? And they found the sweet spot just keeping this distance not so far, not so close to the ball. But, okay. And I can tell you that we spent a lot of time, like maybe 50% of our time, just to find the correct reward function definition. And in the end, we found a very complex reward with a lot of components. It's not really important. The details are not important, but it's you can see the amount of the components, all the components of the system that we had. Once you feel ready to play with your reward function, it's time to implement an algorithm, okay, of learning. Keep in mind that in reinforcement learning, that reinforcement learning itself is quite different from supervised and unsupervised learning. So the iris classification won't lead you to these kind of solutions. And in reinforcement learning, there is a forest of different algorithms specific to the problems. We won't have much time to dive to the details, but this scheme gives you an idea of the manifold of families of algorithms that you can choose from. And as always in machine learning, there are some heuristic to guide you to choose the best one, but usually it's just trial and error. And as always, there is such thing that there is the perfect algorithm, unfortunately. So different algorithms perform in a different way on different kind of problems. So you will need to try out many algorithms until you find the best. But still, let's see the glass half full. That means that probably you will try a lot, you will learn a lot. So I think it's a positive thing. Okay. If you don't want to spend too much time on implementing by your own all these algorithms, there is good news that OpenAI has this repo, baselines, which contains already implemented algorithms. There's also a program interface, so you can just plug it into your environment. And there's a command line interface. You can launch the training just with one command. Let's go ahead. One feature that is shared by all the training algorithms is that the agent starts from scratch. As opposed to a human which plays a game, the agent knows nothing about the physics of the game, have no hint from the environment, and there's no past experience to draw with the optimal strategy. As consequence, the number of situations that an agent must see is really huge. So that's why this slide is called 1 million frames. Usually it's a typical scale required for your agent. On one hand, this partly explains the popularity of games for reinforcement learning solutions. On another, for games, still it's quite annoying waiting a days to see the result on just one single experiment. As you saw before, a lot of experimentation is required for the reward function, for the algorithm, maybe hyperparameters of both, and so on. So the learning cannot take place at real speed. You need to accelerate it somehow. So one possible solution can be cloning several game instances, but still it requires many computational resources. For example, all the rendering part is very resource intensive and absolutely useless for training since we don't use computer vision algorithms. Probably you will also need more hardware resources to implement this parallelization. It will cost you also a lot. Another solution can be extracting the game logic from the original game engine. That was exactly our case. The Haxball, as I said before, is written in JavaScript, but the code is obfuscated. So we needed to interpret it somehow, and we needed to rewrite it in Python. This is the right part. It's doable, but it's really time-consuming. But we were very motivated. We wanted to beat our colleagues, so we just rewritten everything. And once you did it, you can obviously parallelize it. So you can accelerate all the process. Okay, but let's say you have found a reward function that seems perfect. You found an algorithm that performs well, and so on. The time is acceptable. Okay, so what can go wrong here? Okay, actually, we saw in our own experience that we can reach some very cool results after some time of training, and they are really impressive, but they're hardly superhuman level, unfortunately. Worse than that, we needed, if we waited for more time for training, the agent became crazy, like this. Our interpretation is that the model, given enough time, overfits on its own behavior since it's self-play strategy. So as soon as the agent encounters a situation, it forgets how to act and it starts performing just random actions. Maybe the model reaches at some point a satisfying level, but thus we could think of stopping the training at some point of time, but then it went worse. However, in this framework, there's no consistent way to compare the model with its previous version. This highlights another limitation. If we try different reward functions or different algorithms, how do we choose the best one? What is the correct way of comparison? And the solution can be, I hope, okay, implementing a tournament, which can work in these cases, because several agents can compete against each other, and you can introduce some kind of ranking as a measure of the skill. Being trained against different models, we avoid in this way the overfitting. So an agent develops an optimal strategy, general strategy. But still there is a price to pay, that if you implement more matches, you will probably need more resources. And you cannot run a big tournament on your machine. So after all this work, we arrived to this final configuration of our bot. Basically, we defined the state as we defined 14 dimensions of the state for the coordinates, for the velocities, and so on. At each moment, our agent had 10 possible actions to do, just pressing directions, combinations of directions key, the space to kick the ball, and so on. For the implementation, we used a deep neural network, which had 4 layers of 128 neurons. We used PPO2 algorithm from OpenAI implementation. We first pre-trained the agent on self-play. We needed 4 million frames on 10 frames per second. Here, this FPS is virtual game. It's not real. Seconds are not real. It's virtual time. And after pre-training, we used round-robin tournament for a better strategy exploration. We had about 20 models at the time. So with this implementation, we felt ready to challenge our colleagues. And now we will show you some highlights of the match. And keep in mind that the human player, had never seen the bot in action. Okay. Okay, I must tell you that the bot is the blue one, and the red is the human. Here, you can see just line with predicted reward, the best action, and all these details. Not so fast. Yeah. This is very interesting situation. Still, you can see that it's not perfect because it cannot find the optimal strategy for the ball in the corner. Okay.
Del Milan.
Okay. How do I? Okay. Anyway, that was almost the last slide. Però no, ecco. Allora, just last two things, our repo and the full video. That's all. Thank you so much.
Thank you, Ivan. So if you have some questions, you can have like 2-3 questions, then we can actually go to eat something. So, yeah.
Thank you. So do you think that it's because of the self-play that we have so many troubles with defining the reward function? Like maybe, do you have experience or feelings that if we don't have this self-play, maybe it's like the agent with against the environment, we don't have this big problem?
Yes, because self-play itself is not the perfect strategy. Actually, I can show you this thing. This is the graph. This came from Capture the Flag game implemented by OpenAI. And as you see, the self-play strategy performs almost like a random agent. So what happens actually? When the agent plays against itself, there is the first phase, let's say, when he learns the basics of the game. Then he starts to apply some easy, simple strategies. Since he plays against itself, he knows after a while how to defeat those strategies. So he don't apply them anymore. And in the end, he knows that basically the previous experience is not valid anymore. Mm-hmm. So in the tournament, you solve it by playing with different rewards, different configurations, anything you want. In this case, your bot sees more, let's say, variants of the possible strategies, mm-hmm. and has no way to forget about the basics, let's say.
Okay. Mm-hmm.
I wanted to ask about that graph of rainbow. You have this graph. So that was actually the different strategies, switches from one strategy to that one rainbow graph.
Yeah, yeah.
Okay, okay.
No, that was the rainbow curve is just one of the algorithms. There is a link, but anyway, it's just a comparison of different algorithms. My message from this graph is the axis, you see how that millions of frames.
Yes.
So that was the point.
So the rainbow, let's say,
The rainbow
learns
is just
faster.
The rainbow is just an algorithm which performs better from this paper.
Okay. I know nothing about rainbow, but it looks like it's composed of different strategies, or not?
No. The conclusion that we can make is that it learns much faster, because you see on 44 millions of frames.
That's what I understood. Okay.
Yeah.
Okay. Thanks.
So you said like the agent has no idea in the beginning, like, so it starts taking random actions, right? So
not in 100% of cases, but just to simplify the things, yeah.
Okay, so like my question is, how long does it actually take to train the agent?
How long?
How long does it take to train the agent so that it can play against human?
It depends of hundreds of different parameters. I can also show you that, for example, in these cases, there are millions of frames. If you define different reward function, if you choose different algorithm, you can perform better, but you have to parallelize it on your machine, on some cloud, just to accelerate the training process. So the number of the amount of the time that it needs to reach human level, a superhuman level, is not defined. It's always unpredictable. And to reach the human level, maybe you can reach it in, I don't know, 10 million frames. But then the curve saturates, so you have to wait much more to get the better agent.
Okay.
One last question. So
can you
maybe we can do that.
I saw from your first pictures that the game is like multi-agents, right? And you played one against one. So I know that it's so difficult to switch from a single agent game to a multi-agents game, but are you planning to go further in the hell, or?
Let's say that this can be the next big challenge. I can tell you the truth that just to implement the bot that plays one against another player, it took for us 6 months. But also it was the learning part of the algorithms, just trying trial errors, and maybe we will think about adding this complexity of multiplayer, but there will be other 5 problems, I think.
Okay, thank you.
Thanks a lot. So thanks for coming, and yeah, they are here. I think are gonna stay here. Yeah, perfect. So if you have a question, you can actually keep going afterwards. So now we are having a dinner just right there, like just some small appetizer that is sponsored by Google. So also thanks a lot for Google and Giovanna that also manage all this stuff. So an applause for Google also, guys. And thanks. Beer time.